Hi and a very good morning to Sejuk and Miss Lydia. Today we are going to presenting the gas turbine power plant. Here is our members of the group. My name is Ahmad Izzuddin bin Zainuddin, and the second member of our group is Muhammad Nur Iman, and the last one is Stephanie Sham. We will be representing the Sarawak Energy Berhad. We will be starting with the company background. Sarawak Energy Berhad is a state-owned, vertically integrated power utility and energy development company headquartered in Kuching, Sarawak, Malaysia. It is primary electricity provider for the Malaysian state of Sarawak, serving urban and rural customers across the region. Sarawak Energy has been using gas turbine power plant for many years. The earliest gas turbine in Sarawak, open cycle at Bintulu, were commissioned in the 1990s. Specifically, the Tanjung Kidorong power station in Bintulu originally had open cycle gas turbine units with 33 megawatt each, commissioned in the early 1990s, with additional higher capacity units added later. To continue the presentation, I'm going to explain what is a gas turbine water power plant. A gas turbine water plant is a type of thermal power generation system that produces electricity by using high temperature and high pressure gases to rotate the turbine. In this system, fuel, commonly natural gas, is burned to produce hot gases. These gases flow through the turbine, causing it to rotate. The rotating turbine is connected to a generator, which converts the mechanical energy into electrical energy. Gas turbine power plants are widely used because they can start up quickly, deliver high power output, and are suitable for both industrial application and electricity generation. So, what is the application on daily life of gas turbine? Gas turbines are important in real life because they are reliable, efficient, and highly flexible compared to many other power generation systems. One major advantage of gas turbine is their fast startup capability. Unlike coal and or nuclear power plants, gas turbines can start within a short time, making them very suitable for meeting a sudden increase in electricity demand, especially during peak hours or emergencies. Gas turbines are widely used in many applications, including electricity generation, aircraft engines, and industrial plants. In power stations, they are commonly used in combined cycle power plants, where waste heat is reused to improve efficiency. Another important reason gas turbines matter is their use of cleaner fuels, such as natural gas. This results in lower emissions of pollutants compared to coal-fired power plants, helping to reduce environmental impact. Overall, gas turbines play a key role in modern and flexible energy systems, supporting reliable power supply, industrial growth, and transportation needs.
This slide explains the basic principle of thermodynamic flow process. A flow process occurs in an open system where both mass and energy cross the system boundary. In a gas turbine, the system operates under steady flow conditions. This means the mass flow rate is constant with time, and properties at the inlet and outlet do not change. There is also no accumulation of mass or energy inside the system. This steady operation allows us to analyze the gas turbine using thermodynamic law. This diagram shows the overall process flow of a gas turbine power plant. Fresh air enters the compressor. Fuel is added in the combustion chamber and hot gases expand through the turbine. From step 1 to 2, work is done on the system in the compressor. From step 2 to 3, heat is added in the combustion chamber. From step 3 to 4, Work is produced by the turbine. Finally, heat is rejected to the surrounding through the exhaust gases. In process 1, atmospheric air is drawn into the compressor and compressed to a higher pressure level. As pressure increases, the air temperature also increases due to compression. This process requires work input, which is supplied by the turbine through a common shaft. The primary function of the compressor is to raise the pressure of the working fluid to enable efficient combustion. Thermodynamically, this process is modeled as ideally isentropic compression, where entropy remains constant and no heat transfer occurs. In process 2, high pressure air enters the combustion chamber where fuel is injected and mixed with the compressed air. Combustion occurs at approximately constant pressure, resulting in a significant rise in temperature. This process represents heat addition to the system, increasing the specific enthalpy of the working fluid. The high energy gases produced here are essential for generating turbine work. For a thermodynamic standpoint, this is a constant pressure heat addition process. In process 3, the high temperature, high pressure gases expand through the turbine stages. This expansion converts thermal energy into mechanical work, causing the turbine shaft to rotate. A portion of the turbine work is used to drive the compressor, while the remaining work is delivered as network output to the generator for electricity production. This expansion process is ideally isentropic, meaning it occurs without heat transfer and with minimal energy losses. In process 4, the gases exit the turbine as exhaust. Although expansion has occurred, the exhaust gases still retain residual thermal energy. This excess heat is rejected to the surroundings, which is necessary to satisfy the second law of thermodynamics and complete the
Second law,
Brighton cycle.
second
The
law of
system then
thermodynamics.
returns
So
to
the
its
second law of
initial state
thermodynamics
for
explains
continuous
the direction of heat
operation.
transfer and energy
Thermodynamically,
conversion
this
in a
stage
patient.
is characterized
Heat
as
flows
constant
naturally from
pressure
high
heat
temperature
rejection.
source to a low temperature sink. It is impossible to convert all energy into useful work. Some energy is always rejected as waste heat. This law applies to all cyclic devices such as heat engine. So the second law of thermodynamic in cyclic device. A cyclic device is a system that returns to its initial state after one complete cycle. The network output is obtained only when heat is transferred between two reservoirs. A cyclic heat engine must absorb heat from a high temperature reservoir and second reject heat to a low temperature reservoir. 100% thermal efficiency is impossible in a cyclic device. So this is DS diagram for our equipment, which is a gas power gas steam power plant. So at uh, phase 1 and 2 is isentropic compression. So the vertical lines show a constant entropy where air is compressed in the compressor, causing temperature and pressure to increase. There is no heat transfer ideally. So from phase 2 to phase 3, which is there's constant pressure heat addition. The curved line label P equal pressure equals to constant where heat Qin is added in the combustion chamber. So there is increase in temperature and entropy. So from phase 3 to phase 4 is isentropic expansion, whereas the vertical line shows that there is constant entropy. So hot gas expand in the turbine, producing work output while temperature decreases. So from phase 4 to phase 1, which is constant pressure heat rejection, the line level P equals constant, whereas Q out is rejected to the surroundings, reducing the temperature and entropy, completing the cycle. So for the network output of the cycle, that means when the turbine whereas the turbine produces more work than the compressor consumes. So the network output is equal to turbine work minus compressor work. Network is converted into electrical energy by the generator. Due to energy losses, network is less than input heat energy. So the relation of our equipment to second law of thermodynamic is not all heat supply can be converted into work. Some heat must be rejected as exhaust. Entropy increases due to combustion, friction, and irreversibility. So this limits the efficiency of the gas turbine. So here is the equation of efficiency, where the general equation is work net over Q in. So the equation in terms of heat transfer is 1 minus Q out over Q in. Whereas in ideal Brayton cycle, the equation in terms of temperature is 1 minus T1 over T3.
This diagram shows a gas turbine with a regenerator to improve efficiency. After air is compressed, it passes through the regenerator instead of going directly to the combustion chamber. The regenerator uses heat from the hot exhaust gases to warm up the compressed air. Because the air is already hot before combustion, less fuel is needed to reach the required temperature. This reduces heat input and fuel consumption. The turbine still produces almost the same power, but with less fuel used. Therefore, the overall efficiency of the gas turbine system is increased by reusing waste heat from the exhaust gases.
So, in conclusion, the second law of thermodynamics covers the cyclic device because turbine power plants operate on the Brayton cycle. The energy losses are unavoidable in the real system based on the second law of thermodynamics. So, the understanding of the second law of thermodynamics helps us to improve the power plant efficiency. So, the efficiency can be improved by recovering exhaust heat using a regenerator.